Hello, I'm Susan Nash, AAPG, and we have a groundbreaking and very exciting webinar today. And it's put together and hosted by the Energy Minerals Division. So I just want to encourage you to join if you are not a member already, and also to come to Image because we have a number of Energy Minerals Divisions events. And I'll let Nicole Wagoner talk about that a little bit further. But at any rate, I know that some people are updating their Zoom, so we'll kind of get started a little bit. If you give people a few seconds, but again, this is an APG Academy, Enhanced Geothermal Systems, Subsurface Characterization, Resource Evaluation and Development Challenges. It's sponsored by Halliburton, so thank you, Halliburton, and it is put together by the Energy Minerals Division. So right now we have, our speakers are Javs Aljubran and Justin Birdwell and Eric Stautberg, who are all working right now in researching in geothermal energy and in enhanced geothermal systems. And we also have Nicole Wagoner, who's also researching in geothermal systems. And she is our president or the chair of the Geothermal Committee of the Energy Minerals Division. So welcome, Nicole.
Thanks, Susan. Let me go ahead, share my screen.
Yes.
All right. So Susan mentioned I'm the chair of the AAPG Geothermal Committee.
You still need to share your screen.
What was that?
You still need to share your screen. I'm not seeing your screen.
Sorry about that. There we go. As Susan mentioned, I'm the chair of the AAPG Geothermal Committee. We're part of the Energy and Minerals Division in AAPG. And we're not necessarily a new committee, but we're a relatively small committee, so you may not be familiar with us. So just wanted to take a few minutes to introduce you all to the committee and some of the initiatives that we have going. So we've got several people that are helping out with the leadership of the committee right now. Myself as the chair, David Wallace is our vice chair. Gabe and John are helping us out with technical events, and Mayank is helping us as the Gulf Coast rep. We've kind of organized the committee into several different initiatives, the first being technical events, similar to this webinar. So we're focusing on doing a lot of different conference events, workshops, short courses, webinars, those things along those lines. We've also focused on trying to build online engagement. We've recently put together a LinkedIn page, so feel free to go over to LinkedIn and search the committee and go ahead and follow us. We're hoping to build out an AAPG wiki page to provide a bit more information on geothermal and the AAPG's Geothermal Committee. We're also trying to build out communications, working on some annual reports, newsletters, Explorer articles, things along those lines, and doing some outreach as well. So both within AAPG and externally. So if you're interested in any of those sorts of things, feel free to join the committee. You can join the committee and just kind of get information about the events we've got going on, or join the committee and be a little bit more active. So if you're interested in volunteering, there is also a QR code for there. So if there's any of those initiatives that I mentioned that sound interesting, feel free to join, and we are happy to have your help. In that, we're also looking for other section and region representatives. A few things that we have coming up. We're organizing a short course for Image focused on exploration and development aspects. We've got a great lineup of different folks from the industry as well as from academia. So we hope that if you haven't already signed up, that you'll join us on Monday right before Image. There's a QR code there if you want to take a quick shot of that to get a little bit more information on what we're planning. Lastly, we've got a post-convention workshop that we're also organizing focused on techno-economics. We also always have a lot of interest in that from folks. So we're going to do an afternoon workshop on the Friday after Image. So if you're interested, go ahead and join for the post-convention workshops. So with that, I just want to say thanks you all for joining us today. We've got this webinar and we have a few others planned in the future. So go ahead and follow us, and you'll hear about all the latest and greatest things that we have planned. So I will turn it over to Eric.
Well, good morning, everyone. Thanks for attending today, of course. Well, I guess it could be good afternoon, depending on where you are in the country. We have quite a few people here today, which is great. Let me get the laser pointer queued up here. All right. My name is Eric Stautberg. I was asked to do a quick introduction on geothermal energy and kind of an overview of different geothermal systems. Can everybody see my slides fine?
Looks great, Eric.
Perfect. Oh, good. Got a thumbs up. And like I said, my name's Eric Stautberg. I'm a PhD candidate at Colorado School of Mines in the Department of Geology and Geological Engineering. And I'll be going through a quick overview of different types of geothermal systems today. A little bit of background on me. I'm doing my PhD right now in geothermal energy on the Texas Gulf Coast, but I have a bachelor's from Texas A&M in geology, a master's in geological sciences from UT El Paso, and I worked oil and gas exploration for about 7 years, working mainly onshore U.S. exploration. So with that, let's dive into a little bit overview of our current energy portfolio in the U.S. On the left here, this is a map from the Energy Information Administration. It's a great place to start if you're interested in learning everything energy for the U.S. This map shows where we generate geothermal electricity here in the U.S. This is as of 2023, so it's a little dated, but in general, these 7 states in the West is where we actually generate all of our utility scale electricity from geothermal energy. Down here at the bottom, we have just a breakdown on how the different states use and generate their electricity. So for example, down here, California generates 66% of the total geothermal based electricity that we produce in this country, but that only makes up 5% of their total energy portfolio for California. Now for Nevada here, they make up 26% of the geothermal energy we produce here in the US, and that makes up 10% of their energy portfolio in the US. Over here, this is the different fuels we use to generate electricity in the United States. 43% comes from natural gas, 16% comes from coal, and just over 18 comes from nuclear. And then renewables make up just over 21%. But of this total portfolio, geothermal is still less than 0.5% of how we generate electricity in the US. So we have a lot of work to do to really develop new geothermal resources and push this number higher, which is why we're all here today. The last thing I want to show from EIA is just how these different fuels have changed over the past 70 years. We can see coal has been on the decline for the past 15 or so years. Natural gas has kind of taken over for that. Nuclear has been somewhat stable, and then we've been growing our renewable energy sources over the past 10 or 15 years or so. Lastly, I like to talk about just where we sit globally in terms of geothermal energy. And you probably think of places like Indonesia and Iceland as being big geothermal producers, but the US is actually the top geothermal producer in terms of installed generating capacity as of 2023. So go us, but we still have a lot to do because it only makes up such a small percentage of our total energy portfolio. Whereas countries like Iceland, it makes up more of 35% of their total energy portfolio. Even they generate less than we do. We just consume a lot of energy here in the United States. Okay, so let's move into what is geothermal. Geothermal is kind of an umbrella term that means a lot of different things. So of course, geothermal means earth heat or heat from the earth. But there's a lot of different subcategories in geothermal, just like in a lot of things in geology. And so a lot of the figures I'm going to show in the next couple slides come from this GeoVision report. It was published by the Department of Energy in 2019. It's a great reference to start. So if you're interested in getting into geothermal and want to learn more, I would say, start with the GeoVision report. It'll really get you jump started there. So the first thing you're probably familiar with geothermal is conventional hydrothermal. This is what you probably think of when you think of places like Hawaii or Iceland or Indonesia, places with active volcanism. And these are the very hot, very permeable conventional resources that we can develop with existing technologies. So think about drilling wells, producing steam out of the ground, and using that steam to spin turbines and generators to make electricity. And that's conventional hydrothermal. And what we're going to be focused on today are enhanced geothermal systems. And these are more of the unconventional side of geothermal resources, where the subsurface is hot, but maybe not quite as hot as conventional hydrothermal, and we have low permeability or low fluid saturation. So we're going to have to hydraulically fracture these rocks to make geothermal reservoirs. And typically we're doing this in hot, dry rock. So if you've heard of hot, dry rock geothermal, this is what we're going to be talking about today. Advanced geothermal systems, these are closed loop wells that circulate a working fluid underground within a fully cased well to extract thermal energy. We're not going to be diving in this today, but it's quite a bit different than these enhanced geothermal systems. Sedimentary geothermal, very similar to the other two, where we're kind of using these deep brines that are stored in sedimentary reservoirs in sedimentary basins for power generation and direct use applications. And then super hot rock geothermal. This is the really hot stuff, going after superheated rocks above 400 degrees C. Again, we're not going to be getting into this today. We could probably teach a webinar on each one of these geothermal systems, but we're going to be focused on EGS today. But the one thing that all of these systems have in common is we call them blind geothermal systems. So these are subsurface geothermal systems with no surface expression. There's no hot springs, there's no fumaroles, no geysers, things like that. We typically see that with our conventional hydrothermal systems, although we're exploring for these conventional systems that don't have these surface expressions. But whether it's EGS, AGS, sedimentary, or SHR, we don't typically have that surface expression. Okay, and so in types of geothermal reservoirs, this was kind of eye-opening to me when I moved from oil and gas into geothermal. It's really all types of rocks, which was a little surprising to me. I was thought, oh, this has to be all in igneous rocks. And so, of course, with our super hot rocks, since we're going after very, very hot rock that's typically associated with active volcanism, that's going to be mainly in our igneous rocks. Our conventional hydrothermal can be igneous, metamorphic, and sedimentary. Our enhanced geothermal systems that we're going to be talking about today are hot, dry rock, mainly igneous and metamorphic, but we've been discussing, well, can we go after tight carbonates or tight sandstones in these sedimentary basins as a kind of quote-unquote hot, dry rock. In terms of sedimentary basin geothermal, carbonates and siliciclastics are ripe for that, and we can potentially look at evaporites too. And regardless of whatever rock type and lithology we're looking at for these different geothermal systems, fractures are going to be very important for achieving the flow rates we need to make geothermal-based electricity. On the right over here, another figure from this GeoVision report that shows this little thermometer with different temperatures and the different uses, whether it's power generation or direct use. So your super hot rock and conventional hydrothermal really sit at the top here, that really hot rock, and our enhanced geothermal systems and sedimentary basins kind of span that low temperature to kind of low high temperature range. And regardless of the system we're in, we can either generate electricity or explore one of these direct use applications, which we're not really going to get into today. Okay, so the last thing I want to talk about before we dive into EGS are just the different types of power plants we use to generate electricity with geothermal resources. So in our conventional hydrothermal applications, typically we use a dry or a flash steam power plant. And this is where we're directly producing steam out of the ground that can go directly in and spin a turbine, spin a generator, and make electricity. Then we can re-inject that cooled steam or cooled water back underground. In this flash steam power plant, this is where we're typically producing a two-phase system. So we're producing steam and water out of the ground, and we can't send that water through a turbine. So we either have to flash that water to steam, or we have to separate that water out and move it out of the power plant side of the system. And so these are typically the two types of power plants we use in our conventional hydrothermal systems. Now, when we're moving into EGS, AGS, and sedimentary geothermal applications, this is where we're going to be using what's called binary cycle power plants. And these function a little bit differently than these dry and flash steam power plants. So with this, we'll be producing water and some steam or just hot brine out of the ground. We'll run that through a heat exchanger and pass its thermal energy to what we call a working fluid. And this is a low boiling point fluid that flashes to a gas when it's in that heat exchanger, creating pressure. And we use that pressure to spin a turbine, spin a generator, and make electricity. That working fluid stays within the power plant, And whatever fluid we produced out of the ground that goes to the heat exchanger, we can now re-inject underground to be reused again. And so you might have heard organic Rankine cycle power plants. That's typically what we use in this binary cycle world. And what we're actually seeing in the conventional hydrothermal world, that companies are starting to shift to using these organic Rankine cycle power plants in the conventional hydrothermal world, just because of increased efficiencies with these type of power plants. So this is what we'll be discussing for EGS today. So I've said EGS a lot. What is it? The basic concept here is we're going to be using vertical, horizontal, deviated wells, any combination of those, and hydraulic fracturing to engineer a reservoir in hot, dry rock. So this is another figure from GeoVision, and what they're showing here is we're going to build this engineered reservoir down here in this hot, dry rock, and then we can inject fluids down into the subsurface, into this reservoir we've constructed, allow it to move through the fracture system, and then we can extract that hot water or hot fluid up to the surface and run it through one of these specialized power plants to make electricity. And so this is has potential to provide clean baseload electricity or direct use heating, and that's really important. Baseload is an important resource for us. And these projects aren't new. They've been around since the mid-70s. One of the first ones, or the first one, was the Fenton Hill, New Mexico project, which was championed by Los Alamos National Lab. I encourage you to go look up that project. And there are many ongoing EGS projects around the world, with a lot being developed in Europe, but we do have some larger scale ones here in the US that I'm going to be talking about over the next couple slides. And one of the things that's really championed EGS over the past couple of years is just increased drilling efficiency. As you can imagine, drilling into hot, dry rock, multiple wells, is a bit costly and time consuming. And we've really seen a reduction in drill time and subsequent costs, which are really bringing down bringing down the cost of these projects and really pumping up the economics. So that's very exciting. The first project I want to talk about is the Utah Forge project in Utah. It's kind of a field laboratory that the Department of Energy sponsors, and that's where they test out new technologies for characterizing, creating, and sustaining EGS projects. It's located in Milford Valley, shown here kind of in western Utah. And they currently have a couple of wells drilled, 2 deviated wells, a vertical test well, and 3 seismic monitoring wells. And if you look at this figure from their website, you can see how they've drilled a deviated well deep down into the granitic basement. We're in an extensional basin here. We're in the Great Basin, the Basin and Range. So they've drilled through the basin fill down into this granitic basement where it's about 400 degrees Fahrenheit. They've developed a fracture system with hydraulic fracturing, and they have a production well where they can bring that hot water back to the surface to make electricity. So it's a really great project. They have all their data on their website. I encourage you to go look up this one. Another quick project I want to talk about is Fervo Energy and their Project Cape. Fervo is a geothermal exploration and development company operating in Utah near the Forge project. They are looking to develop a 400 megawatt EGS project to provide utility scale electricity, which is really phenomenal. And they're going after that hot granitic basement rock again, beneath those basin-filled sediments. This is a cross-section from Furcho et al. 2024, showing some of the wells they've drilled here at Fervo. Forge's wells are just over here to the east. The maximum temperature they've seen so far is over 440 degrees, and that's after thermal recovery from drilling, so that's very hot. And what they're doing is they're drilling 13,000 foot measured depth horizontal wells in a wine rack pattern with 5,000 foot laterals to try to extract the thermal energy stored in this hot granitic basement rock. And one of the things they've really championed is this dramatic increase in drilling efficiency over the course of the project. This is a days versus depth curve for some of their wells. These 2 red wells, they were drilled in a different basin further out to the west, I believe. But these are the wells drilled here at Project Cape. And you can see how they've really reduced the days worth depth time with this. And I think Jabs is going to talk about more of this later on in the presentation. And so the last thing I want to talk about, since we've introduced EGS now, are just some of the challenges. And these are some of the challenges we see in all subsurface exploration, whether it's conventional oil and gas, unconventional oil and gas, or these different types of geothermal systems. So first, induced seismicity and public concerns are always going to be an issue when we're moving a lot of water through the subsurface. Drilling and plant operations, the surface side of things, keeping these power plants running and things like that are always going to have some issues. Reservoir creation and circulation. So, when we're trying to hydraulically fracture these hard, hot, dry rocks. There's obviously going to be some challenges there. Of course, the geophysics, the subsurface characterization, and the geomechanical modeling. These are problems we have in unconventional oil and gas too. So they're nothing new to us as geoscientists and engineers. And lastly, regulatory and finance. We're still working through a lot of regulatory things across the US alone, let alone across the world. And so these are some issues that we're going to have to resolve going forward. Looks like a lot of problems, but these are just similar issues that we have with all subsurface energy projects. And Jabs is going to dive into these in detail with his presentation. Lastly, I want to show this EGS development map that Jabs has put together. And this is showing the levelized cost of electricity from low in red and orange to high in green and blue across the contiguous US. And he's going to dive into how these maps were made and what they actually mean. But the levelized cost of electricity is a metric we use to understand kind of the economics of these different geothermal projects. And as you can see, there's quite a bit of red and orange across this map. And that gets me excited. That says, hey, there's an enormous resource potential that exists across the US that we have not even barely developed at all. And now we need to figure out how to do this in the subsurface with geology, geophysics, petrophysics, and engineering. So with that, I'll go ahead and pass it off to Justin, and he can carry on.
All right. Thanks, Eric. Let me share my screen here. All right. Thanks, everyone, for participating today. I want to start out by thanking my colleagues at USGS who have really done the lion's share of this work. They include Sarah Gelman, Rand Gardner, Jake D'Angelo, Eric Burns, and Colin Williams. They've all been instrumental in getting this work done. I'm going to be focused on USGS assessments of EGS today, although we have been mandated by Congress through a number of different policy acts to essentially evaluate all different flavors of geothermal across the United States, the territories, basically everywhere that Americans live. So to get going, I want to start by mentioning that our current assessment methodology anticipates that most development of blind systems, as Eric talked about, in particularly in sedimentary geothermal system or sedimentary basins, will require an engineered reservoir or an EGS approach. We have done a test run on this and demonstrated a methodology in the Great Basin. That's a recent assessment that was completed and is available online. The approach yields a provisional resource estimate, and this differs from a lot of our other methodologies. And part of this is just because even though there are EGS systems out there, we don't have enough of them installed to be able to directly relate how those plants operate to the geology. So we're making an informed guess. We have some fairly simplified models for how we're going to evaluate the resource that I'll show. But yeah, just want to say that these are provisional resource assessments and should be taken as such. I'm then going to talk a little bit, once I've gone through the Great Basin assessment and methodology, I'm going to talk about how we're applying that now to sedimentary basins across the United States, how we're basically planning to march across, starting with the lower 48. And we've got a couple of basin models that are built. We have several that are in development. I'll give a quick overview of a couple of them, and I'm going to give a presentation at Image that'll go a little more in depth on some of this basin modeling work. So Eric's already shown the cartoon on the right there. I just wanted to mention that in terms of geothermal resources, this assessment of the Great Basin is focused on electricity. So it's for temperatures greater than 90 degrees C. We're not talking about direct use or heating and cooling. This is just heat that could be used for generating electricity. And obviously, we have a pretty good idea of where geothermal resources are located in the US. We have a variety of different temperature maps and heat flow maps that have been published. This one from Colin Williams and Jake D'Angelo. Obviously, a lot of the installed electricity is already known to be in the West, particularly places like California and Nevada. But we want to be able to develop these thermal resources across the country. And there are some other opportunities. As Eric mentioned, there's supercritical systems in volcanic provinces, a number of deep hot sedimentary basins spanning the center of the US, going from North Dakota down to the Texas Gulf Coast. And then even in these old cold rocks to the east, we're hoping that an EGS approach, drilling to sufficient depths, or using something like log closed loop systems might allow for some electricity generation in some areas. So Eric's already kind of addressed what EGS is. I'm going to just say from the USGS perspective for our assessment purposes, this is a circumstance where you're extracting heat from the subsurface, typically from otherwise impermeable rocks, and you have to engineer permeability. Most of that's probably going to be done by hydraulic fracturing, but there are other approaches to doing this, such as chemical stimulation and thermal stimulation. The idealized system we're going to talk about for our assessment is a doublet with a defined volume that's drilled above a certain depth and at a temperature where you can create electricity. So what is the assessment assessing? What is accessible? Less than 6 kilometers. We're defining that based on the ability to hold fractures open and just it's not necessarily the limit of drilling technology, but the limit of what is viable and likely to be developed. Obviously, we're using a 90°C temperature cutoff. And then there are a number of other efficiency factors that we build into the assessment model. These include things like well distance, which relates to fracture length, the distance between fractures, and then viable geology and some other correction factors that we'll talk about. So what goes into the assessment? In this case, for the Great Basin, there's been a great deal of work. You can see there on the left an updated heat flow map that was generated by our team using inputs from our geophysics staff, a lot of data analysis and modeling, and then also inputs from other organizations like the University of Nevada-Reno and the Nevada Survey. We can then take that heat flow map and calculate temperatures at different depths. In this case, you see one for temperature at a 6 kilometer depth in the Great Basin. And we can then translate that using the temperature, heat capacity, and density to a power density map, which is shown there on the right. And that will be the tool that we use for summing up the thermal resource and evaluating electricity generation potential. So this is that highly idealized geothermal model or EGS model that I alluded to earlier. We're looking at a production well, an injection well, idealized fractures, and we're going to evaluate the efficiency of extracting heat from a system like this. In this case, we're looking at ideal heat extraction for a variety of different well distances and fracture spacings. Again, this is idealized. This is assuming that we can create fractures up to 150 meters or up to 50 meters in length, well distances up to 1 kilometer. And you can see the efficiencies range from maybe as low as 20% up to as high as a little over 60%. Now that will have to be modified to account for the real world, because again, it's an idealized model. We then look at electricity conversion. This is again something based on data where we can look at the temperature of operating power plants versus the conversion efficiency. And that we can actually, in fact, we can just build that directly into the model. And this is the electrical conversion efficiency ranges from maybe 5 to 20%. Now, the other assumptions that go into this that make it highly idealized is we're looking at a 30-year energy production time horizon, and we're looking at steady heat extraction so that we have steady electricity production over that period of time. The idea being you don't want to extract the heat a lot faster earlier, because then you have to overbuild your system for the early electricity production that you're doing, and then your ability to produce is going to taper off as you deplete that thermal resource. So again, back to those efficiencies that I mentioned earlier, we've already talked about electrical conversion and the idealized heat extraction efficiency. These best estimates are the numbers that actually went into the actual assessed values. So the next thing, again, I alluded to this, the heat extraction correction factor. This is related to irregularities in the geology, so heterogeneity of the rock, and then also the fact that even if you're really good at fracking, you're not going to make perfect fractures. They're not going to be perfectly spaced. And so you're going to have something less than the ideal efficiency in terms of that heat recovery. We're using a best estimate of 10%. Reservoir spacing, this has to do with the packing of these systems. And in order for them to not interfere, the halo of each volume of rock, if you were to stack these as spheres within that volume of rock, you can pack maybe, you can get 74% packing efficiency. Now, that could vary if you need a bigger buffer between your systems to make sure they don't hydraulically and thermally interfere. Or if you don't care about interference, you can pack these things closer together and you may squeeze out a little more of that rock for extraction. Now, the biggest area of uncertainty that we have relates to the viable geology. And in this case, like for the Great Basin, we don't really have a 3D lithologic model that we can try to high grade the different types of rock for their geologic viability. So this has the widest range of uncertainty. We're using a number of about 25%, which in some basins, I mean, it may be substantially higher than that. But at this point, that's what we're working with. We take all of this information, we put it together, we take our power density map, we sum up everything that's above 90 degrees C. And for the Great Basin, with our efficiencies all multiplied together, adding up to about 0.5%, we get a useful resource of about 135 gigawatts electric. There are any number of efficiency improvements that might be gained in the next few years that could increase this substantially. For one scenario we looked at, you might get an order of magnitude improvement in energy recovery with some reasonable advances in technology, things that are likely or possible to happen. One thing I should say about that 135 gigawatt electric number, though, that's roughly 10% of what the US currently uses or currently produces. So it's not even that with that 0.5% efficiency of recovery and usability. It's pretty good. That's a lot of electricity. You can find our fact sheet here, get a QR code, get the laser pointer out of the way, or you can use the DOI number there, or you can just search for fact sheet 2025-3027, and it'll come right up if Google is working. So now on to the basin modeling portion. As many of you know, there are a variety of basin modeling tools that are out there. There's a ton of data that's out there, particularly on petroliferous basins that have been drilled to death, like the Gulf Coast, in which case you can pretty readily take these available data sets and build 3D temperature models. We can then take those 3D temperature models, like we've done with the Great Basin and our highly idealized EGS assessment approach, and we can evaluate the EGS potential. Now, there may be units within these formations that would be considered more conventional hydrothermal or conventional geothermal because they already have permeability. But for purposes of this talk, I'm not going to get into differentiating impermeable versus permeable mudstones and other sedimentary rocks. We're just going to focus on the EGS part. So we have structural and lithologic inputs that we can build into these models based on well logs and other types of data that have been generated over the years. We have a large number of formation tops in a lot of these basins, and then tens of thousands of direct temperature measurements, which come in very handy. Now, one thing with those temperature measurements, most of what we have is bottom hole temperatures, and anybody who's worked in wells knows that circulation of mud is going to cool the well down, and so the temperature you get is not quite exactly what the reservoir temperature actually is when it's equilibrated. So you have to use a correction method, and we've tried a couple of different ones, and I'll briefly mention a few of them later. But we've settled on an approach where we're actually using the heat flow modeling capability of the software we're using to take that raw data and basically cut a correlation across the data cloud for these pseudo wells where we've lumped 6 square miles, 50 square miles, depending on the resolution of the model. All the wells, we look at a depth temperature profile, and we try to find a heat flow scenario that kind of cuts across the top of that data cloud so that we get what we think is a reasonable estimate of the actual temperature, but it's a conservative estimate. We're not overestimating the thermal resource, which is not something we want to do. Some of you may have seen a basin model recently published by Sarah Gelman in 2024. There was a marine and petroleum geology paper that outlined the overall basin model. And then more recently, her and Eric Burns have published a geothermics paper looking specifically at the geothermal applications of her basin model. And obviously, Williston's been drilled and drilled and drilled, so there's a ton of data. We get great structure control. We're able to create maps, several different types of outputs from the basin modeling software. So here on the left, you can see that's the temperature at a 3,000 meter burial depth in the color contours. On the right, the color contours represent the depth to 150 degrees C. And these are just a couple of examples of the kinds of outputs that you can get. We've also looked at the DJ Basin in Colorado, Wyoming, and Nebraska. We've also got great inputs for this. We're using the basin province outline from the USGS, partly because we've got to define the basin extent somehow, and it seems like everybody does it a little bit differently. And we're USGS, we already have our own boundaries, so we just use those. We have tops for roughly 79,000 wells from S&P, basement maps from the Colorado and Wyoming surveys, a variety of regional cross sections. Some of the best ones are in the RMAG Big Red Book from 1977. And then, as I've mentioned, we're gridding the area up for looking at heat flow. Now, in this case, there was actually a basin specific temperature correction model that we used from Ann Crowell and Will Gosnold up in North Dakota, or University of North Dakota. Going forward, we will be using the heat flow approach pretty much exclusively, but this was something we had ready at hand, and this was one of the earlier models we looked at, so we went with this Forster correction. We also had new inputs of paleo-environmental maps from the Denver Museum of Nature and Science that we were able to basically relate to rock lithologies on a regional basis. So we took these maps from the DMNS, we carved out the DJ Basin. You can see there's a variety of different depositional settings within any of these particular time slices. And we then used that and translated it to a lithology. And we're able to actually build that into the 3D basin model. So here you can see we have our structure, our formation tops, and our lithofacies variability all laid into this 3D model. Some of the outputs from that, this is kind of a combined set of maps where on the left, you can see these are the dashed line contours are the depth to 90 degrees C in feet. The color contours show you the formation you're in, which might be useful to know if that formation has particularly good rock properties for your application. And then the map on the right just shows where the 150 degrees C cutoff would be for the same basin. We've done a similar thing in the US Gulf Coast, where we've taken maps from Snedden Galloway, from the Gulf Depositional Basin Synthesis Project at UT Austin. And so we've done a similar thing looking at lithologies and the distribution of rock variability. We started out in this model using a Waples correction, but we found that that gave us more or less a uniform 20% shift in temperature based on time state circulation. And only about 10% of the wells actually had a TSC value. So this is where we ended up redoing the model and have gone back to this, or have gone to this heat flow modeling approach. So again, the outputs are, they can be pretty basic, like this one showing depth to 150 degrees C and what depositional unit you're in. Or you can extract for a particular unit if it's got a lithology that you think is amenable to your type of project. You can then look at the isotherms and see where you need to be roughly to hit whatever your target temperature is. So in closing, we're basically planning to march across the lower 48 over the next couple of years, doing EGS assessments in every sedimentary basin, eventually using a national temperature map to fill in the gaps between these said basins where there's a lot less drilling data. We have found basin modeling to be a great tool for integrating data sets in said basins and evaluating geothermal resource potential. And again, we're looking at this on a regional scale, but you could dive deeper and do more detailed modeling with more types of data, kind of shown there in the fourth bullet. So there's a lot more that could be done with this. And again, the visualizations and model outputs, you can tweak them to your particular need or the particular type of information you want to show, and that's really handy too. So I guess we're holding questions till the end, and I will hand off to Jabs.
Thank you, Justin. Much appreciated. I suppose that you can see in my slides, so I'll kick off and get into it. My name is Jabs Aljubran. I'm a geothermal researcher at NREL, and I work on geothermal mapping and modeling of next-gen geothermal systems. I hold a PhD from Stanford University, the geothermal program out there as well. And prior to my PhD, I spent nearly 5 years digging holes and fracking rock in oil and gas. The focus of my talk here is on the techno-economics and subsurface challenges aspect of EGS in particular. And I want to start by introducing the concept of LCOE, or levelized cost of electricity. Eric talked about it, which is great already, but to be on the same page, it's an economic metric that's defined as the total lifetime cost over the total lifetime generation of a system. And it's very useful to compare different EGS projects where lower LCOE is definitely better. Now, one practical research question that I asked during my PhD at Stanford was, what is the levelized cost of electricity of EGS across the United States? And this is the same question that we look a lot at NREL as well. And answering this question really involved developing a thermal earth modeling framework in the lines of what Justin described. In this case, it's using physics-informed neural networks to predict temperature at depth. And since I joined NREL, this model has been updated to reach depths down to 20 kilometers. Also, I developed a techno-economic model that is the flexible geoeconomics model, FGEM, that you can see in the center. And if you feed the temperature predictions into this techno-econ model, then really you get results of economic potential in terms of LCOE, as well as return on investment or ROI. And I want to look into this in more depth before I get into the challenges of EGS. In particular, a big component that Eric touched on when it comes to EGS overnight CapEx is drilling. It accounts for about 30 to 60% of the overnight CapEx spending in EGS. And recent work by Forge and neighboring commercial projects deployed oil and gas drilling technologies and showed significant improvements in drilling costs. They brought it down from about $1,000 per foot to about $400 per foot. That's about or over 50% improvement in drilling efficiency. Now, to understand the sensitivity of LCOE across the country to drilling costs, we consider two cases, one with the 2022 drilling rates and another one with the 2024 drilling rates. Starting with the relatively less efficient 2022 drilling rates, this map shows the minimum LCOE across depths at a given location across the US. Blue is high LCOE, which is less favorable. Red is more favorable, that is lower LCOE. The average market price for 1 megawatt hour is $70 if you're selling hydrothermal power. So anything that is yellow or orange or red is profitable on paper. The conclusion here is that EGS is cost competitive in the Western US, even with relatively less efficient drilling rates of 2022. Now, considering 2024 drilling rates, the entire country lightens up. And this is a map that Eric showed earlier, and this is really where it comes from. So EGS, in conclusion, is cost competitive over more than half of the United States. But just a reality check, does this mean that we're already generating EGS power at 40 to 60 US dollars per megawatt hour? Really, the answer is no. We are not fully there yet in terms of technological development. There are a few challenges to overcome. So what we found through this work was to arrive to this LCOE map that I just showed, you would need to tap into very hot rock that is over 300 Celsius, and you want to produce at over 125 liters per second and get the thermal longevity of these EGS well pairs to be at least over 15 years, even better, over 20 years. So the other reality check here, do we have the technologies required to achieve these parameters? And the answer, I would argue, is mostly yes. And we'll go through some of these technologies. We're going to stick our heads in the subsurface. We're not going to be talking about the surface facilities that are power plants. It's out of the scope of this presentation. So if we sketch an EGS well pair, pretty much you have a piece of rock that's over 300 Celsius. You drill a couple of wells in there, horizontals, you install casing, you cement it in place, and this process involves drilling bits, fluids, pipes, directional drilling equipment, casing, cement, and many other tools. So this process involves various levels of challenges and opportunities, like I lined up in this table, and I'm going to briefly touch on those without spending too much detail. So the first thing is drilling bits or mechanism. Again, drilling is 30 to 60% of the total cost. The current EGS projects are using conventional rotary drilling methods, which are readily available from oil and gas. And I earlier showed how Forge and neighboring projects managed to achieve improvement of over 50% in drilling cost. A lot of what they did had to do with optimizing drilling parameters and using polycrystalline diamond compact bits, or PDC. And these are effective in pretty much break-in abrasive basement rock that we deal with in geothermal. Now, another mature drilling technology uses a hybrid, like this animation you see, that is rotary percussive drilling. It pretty much, in addition to rotation, adds a piston and a hammer casing that pneumatically impacts the bit into the rock, and it makes it drill more efficiently depending on how you design it. There are other emergent technologies involving pumping steel particles, as well as energy drilling using plasma and millimeter waves. Now, when it comes to cleaning the wellbore as you drill and maintaining cool temperatures such that your equipment can survive the drilling operation without thermal stresses, cracking, and damage, drilling fluids come into play. They're very important. We have drilling fluids available in the market up to temperatures of 350 Celsius, water-based, yet their performance is not validated for cleaning cuttings when drilling inclined or horizontal wells like we do in EGS. Now, of course, insulated drill pipes are very important, and they're very effective in managing downhole temperatures. This plot to the right-hand side shows actually the temperature profile of the rock in orange at the Kakunda superhot well. And a group of researchers from Akita University, they modeled the effect of drilling that borehole with insulated drill pipe and without, and they found that using insulated drill pipe can bring temperature down to less than 100 Celsius, which is amazing. Now, there are different ways to insulate drill pipes. Some propose titanium, which has 4 times more thermal resistance or insulation compared to carbon steel, for example. Others proposed vacuum insulated tubing or drill pipes, and also internal and external coatings applied to the drill pipes. Now, temperature management is very important. If you want to drill horizontally, what you deal with is management while drilling tools, or MWD, that are rated to 210 Celsius. So you better cool down the wellbore to conditions below that, or do more research to get the MWDs to temperatures higher than 300 Celsius to exploit the systems of interest. Now, casing failure and cement failure are 2 other common problems in developing very hot resources. A lot of these failures are promoted by mechanical, thermal, and chemical processes in these sort of operations. And it doesn't stop at the casing string, but also has to do with the connection, which is a very weak point in the casing. And when it comes to cement, there are different solutions people propose to, for example, lower the density of the cement using microspheres or foam-based formulations to avoid cement losses into the rock. And just in general, I think there is like significant need for developing such formulations that can withstand thermal and mechanical cycling in EGS environments. The other thing besides wellbore construction is stimulation and production. After you drill, you want to create fractures and you want to circulate water to extract heat. Now, there are a lot of challenges, once again, and we want to run through them in brief. One of the main technologies required for stimulation is multi-stage zonal isolation. In oil and gas, the 2 common ways of achieving that when hydraulically fracturing a well is plug and perf, like you see on top, and ball activated sliding sleeves. In Forge and other projects, they used plug and perf so far, which is rated to less than 250 Celsius because it uses elastomers as well as guns and explosives to penetrate through the casing and create fractures. Sliding sleeves, on the other hand, they are just mechanical valves you install alongside the casing. You draw balls and you activate them one by one. And as you activate them, you apply pressure again and you create fractures. Now, some of these sleeves, like the ones on the bottom left, are made of metal to metal seals, meaning that they're rated to over 400 Celsius, and they have been demonstrated in EGS recently in wells with over 300 Celsius. Other techniques are more creative in a sense, where they propose to use electric current or hydrojetting to create fractures. So there's room to improve and develop in this arena as well. Proppants are extremely important to keep the fractures open. In oil and gas, the most commonly used proppant is silica sand, which is fine for a lot of standard conditions, but when it's exposed to high stress and temperature, then it gets crushed and becomes unstable. So there are many options in oil and gas that were developed for high pressure, high temperature applications with good crush resistance, thermal stability, and also proppant bed or pack conductivity. These could be repurposed for geothermal or improved. But again, cost is an important factor just to make sure that we hit that $40 to $60 per megawatt hour in EGS. The other aspect is production. I showed this plot and the fractures look beautiful, symmetric, almost identical, but in reality, you get some fractures that are more conductive than others, and they take more or most of the flow. That's always possible. So you want to prevent it from happening, or if it happens, you want to intervene and fix it. This is pretty much called thermal short circuiting, which means that the injected cool fluid reaches the producer too soon. This non-uniformity across fractures was observed in a spinner log measurement that was taken by Fervo at Project Red. And here's the injector lateral on the bottom. And these are stages of fractures. And these bars represent flow across each stage of fractures. And we see the biggest bar is about 10x the smallest bar. Well, this is common also in oil and gas. It's nothing new. What this says is that, hey, it's one area that we can work on. It's one challenge that we have to tackle to improve how we develop these systems. And there are different solutions that people have been proposing and working on. One family of these solutions is flow control devices. The one on the left-hand side is pretty much using a flow control mechanism that is integrated into a stimulation system based on sliding sleeves again. The one on the right-hand side rather uses an interventional flow control technique where if you detect the problem, then you want to go and install it. And of course, temperature rating is important here, such that you are all metal versus you have packers or you don't. Now, the last two bits I want to touch on briefly, which really it's unfair to spend 2 minutes on these two. I think you could spend another 15 or 20 minutes on numerical modeling and seismicity. But very briefly, we care to model all 4 processes in EGS that are THMC, thermal, hydraulic, mechanical, and chemical processes. We care to model the stimulation phase, which is when you create the fractures, as well as the production phase, where you produce and extract heat. Reactive processes in particular are challenging, I think, involving solubility, precipitation. They could damage hydraulic conductivity across fractures. They're not easily predictable and require a lot of knowledge in geochemistry as well that you would have to incorporate into the model for your specific resource or prospect that you're developing. Also, thermoelastic stresses could cause the fractures to evolve over time, and that's another problem that is needing much attention. Last but not least, understanding and monitoring induced seismicity is crucial across geographies and geologies to de-risk EGS development and get improved or better public perception of these operations. Of course, there's a number of studies that have been looking at sort of different aspects of induced seismicity when it comes to development at higher temperatures. A lot of work done by the Clean Air Task Force when it comes to super hot development, for example, and what it translates to for induced seismicity. There's the brittle ductile rock behavior that could dampen down the seismic effect or maybe could result in a very different fracture network created hydraulically. And that area requires a lot of lab as well as modeling work to further understand. Of course, field measurements and operations around induced seismicity are much needed to really supplement and support EGS developers with templated protocols and procedures and strategies on how to proactively reduce seismic risk and tackle it if it occurs at any level. And with this, I would like to pass it across to Susan.
Thank you. Well, we've had a lot of questions answered in the Q&A, and we have time for some more questions, but I just want to mention again that everyone who registered will be receiving a copy of, or an email with a link to the recording. So if you have to go and we're still answering questions, you can access everything. And I just want to take another moment to thank or invite our presenters to turn on their cameras. And I'd like to thank Nicole Wagoner at the University of Reno, Nevada, who is the chair of the Geothermal Committee. I'd like to thank Eric Stautberg, who's at Colorado School of Mines, and Justin Birdwell, who is at USGS, and Jabs Aljubran, who's at NREL. So at any rate, we have a lot of questions, and I think that before I start facilitating any of the questions, I would like to see if Eric or Nicole or Justin or Jabs, if you saw any questions that you answered that you thought were particularly important. Justin, go ahead.
So one of the things I forgot to say on one of my slides was that 30-year time horizon, that's based on that's essentially controlling the flow, controlling the system such that you're extracting heat at a steady rate until you reach that temperature threshold for electricity, or not, basically 90 degrees C. So you are going to bleed down the thermal resource over that 30-year period until the temperature reaches about 90.
Okay, that's good to know. And I noticed that there were quite a few questions on the thermoeconomics, et cetera. Nicole, would you like to respond to some of those? So basically asking about the potential, like the costs of if the costs are coming down and some of the challenges, or let's see.
Yeah, Susan, I'm probably not the best one to answer those questions. I'm not an expert with technoeconomics. If anybody else wants to chime in on those, we can, but I'm happy to point everybody to our technoeconomics workshop that we're having speakers on.
That's what I was thinking of. So
last Friday.
I'm sorry about that. That's the thing I was thinking of. Well,
Yeah, I'm more of a conventional geothermal geologist, so not necessarily my realm of expertise.
okay, thank you.
I just have maybe a short comment on that, and maybe Jabs can help me out here. But with a lot of these geothermal projects, they deal with a high upfront cost. And the way I like to think of it in my mind, compared to these other projects like coal, natural gas, nuclear, oil and gas, wind, solar, you're buying all your fuel up front by drilling all these wells, doing these big completions, installing these power generation facilities. You have all these high upfront costs. So it's kind of mitigating that. And I think what we've seen just in the past 6 to 12 months, dramatically decreasing the time it takes to drill through these hard, hot, dry rocks is started to lead to that, increase efficiency and kind of what Jabs was showing with those maps, with better drilling rates, we can really bring down these costs since there's so much upfront costs associated with these projects.
Yeah, I'll jump in just to add to what Eric said. I agree 100%. I was just scrolling down the questions on technoeconomics, and there are a couple of interesting questions. One was on whether or not the maps that Eric and I have been showing include subsidies. And the answer is yes. These include 30% investment tax credits in these calculations. And I would like to refer you to the original paper that we've been referencing in these slides that is out in Nature and really discusses the exact assumptions of it all. The other question, which I thought was interesting, was how ROI, or return on investment, could be different in places like Texas. I want to emphasize that on the western side of the country, the ROI map that we had in there was for about 20 years timeline, and it was close to 350 to 400% over the lifetime, which translates to about, maybe if you do the math, some 16 plus minus percent. Now, if you go out and look at the bankability of this kind of project, investors in the energy sector, they put money in solar, for example, when they expect ROI of about 15%. So it's already there in terms of a $70 per megawatt hour power purchase agreement. The recent EGS projects have been signing PPAs closer to $100 per megawatt hour. So this tells you that the 16% I just quoted of annual ROI could be even higher, depending on the PPA nominal price that you end up signing.
Okay, great. And I think that this was probably answered during the presentation, but it kind of ties with other sort of affiliated questions like how do you find EGS candidates, et cetera. What is the most successful EGS project producing to date?
I can chime in and just say that to date, we don't have power that is coming out of EGS, like fully producing EGS power plant. We're very close in a number of fronts, and I think Fervo is charging forward in that sense in Utah. A number of those have been commissioned, but we've done a lot of EGS drilling and fracking over the past 2 decades, which has taught us a lot and put us where we are today with good progress in techno-economics.
That's
Yeah,
a good
I
question.
think that's the exciting part of where we are. We're kind of on the cusp of figuring out these resources. We've really just started in the past 5 to 10 years trying to develop these EGS resources on like a utility scale. Everything else, a lot of them here in the US have just been, kind of a science experiment. There are some projects going on in Europe that I'm less familiar with, and maybe the panel is here that I encourage some people to look up. And the Pollock et al. 2021 paper that I quickly showed on one of my slides, that does a good job of chronicling these different EGS projects on a global scale. So if you can find that paper, maybe we can post it on AAPG's website, but that does a good job of giving an overview of all of the EGS projects that have been completed globally in the past couple of decades.
Excellent.
Yeah,
Okay,
And
and
honestly, some of
I'll
the
add,
EGS, the last thing I was going to say, some of the EGS projects, they're more focused on direct use too. So just using the hot water for its thermal energy and not to generate electricity. And so there are some ongoing successful projects like that in Europe, I believe.
and I'll add in there too that Fervo does have a project online in Nevada near Blue Mountain. So that project is generating a few megawatts, I believe, still.
excellent. Okay, so here's an interesting issue that ties into the water issues. When one fracks into a dry formation, are you expecting an inflow of interstitial water to cycle in the geothermal process, or do you expect to inject new fresh or salt or brackish from a different source?
I can say something quickly about that. We did not account for the need for water in the EGS assessment of the Great Basin, but that is a concern because these rocks may be dry and there may not be available surface water to actually build out a system. And then if you inject a bunch of water and lose it through a fault or something, you're really potentially going to be in bad shape. So that is a concern in areas like granitic provinces or places where you're not talking about formations that have indigenous or formation waters to circulate.
Okay, good. And then that kind of ties into issues of induced seismicity and all that, which ties into a question, are big parts of Oklahoma and Kansas showing overall less potential because of risk of more induced seismicity?
I can just quickly say we've done some preliminary modeling of the Anadarko Basin, and some of it's just that it's deep and cold. It's an older basin. You've got to drill pretty deep depths. I'm less familiar with the situation in Kansas, but it may be a similar thing that it's just the depths you'd have to drill to may be substantially higher than in other areas.
Man, I'll just add that there are issues of people thinking about co-producing geothermal with the produced water in a lot of especially those that have a high volume of water that they're producing. And that's being investigated now.
Yeah, there's some interest in places like the Salton Sea and the Smackover for combination lithium extraction and geothermal recovery. And yeah, hopefully some of those projects will be going. I think the Salton, there may be activities already underway, but yeah, definitely an exciting thing. And there's projects in the UK looking at similar dual use applications.
Yeah, I wanna chime in and add to that. I agree 100% with respect to Oklahoma and Kansas. The modeling that we've been showing doesn't really look into seismicity per se and quantify it in dollar signs, but rather, like Justin said, the potential that's being shown out there is a function of how deep you need to go and how hot it is, aka geothermal gradient. But for, again, what we've been showing is for power generation. It doesn't mean that, hey, you know what, there are no other applications or different designs where you can exploit this in different means. NREL does look at using or repurposing oil and gas wells in Oklahoma in particular. I've done a couple of projects already that are out there to understand its viability for heating purposes in particular. So definitely there's more room to look into how to use geothermal.
Really good point. Yeah. Let's see. And I think that some of that applies to the Permian too. Heat potential very low in Permian Basin. Is that because of thick carbonates or water flooding? And the question just popped away, so I didn't finish it. But anyway, can you speak to the potential in the Permian? I think it's the same issue, isn't it? That where there are direct use potential, but it's not hot enough for.
Yeah, I mean, a lot of the central U.S. basins have cooled quite a bit. That's why once you get over to the Rockies, you know, a lot of the Laramide basins are hotter. Piceance, oddly, well, not oddly, it was just surprising to me, is potentially is a good potential geothermal target because it's pretty hot, and there are hot spots in Uinta. But the further east you go, the more of this like old cold rock problem you have, where these basins have been there a long time, and a lot of that thermal energy is dissipated through the rock column, and that really limits their potential unless you're willing to drill very deep. There was an Air Force project in Central Texas around San Antonio that they were talking about drilling 20,000 feet into the basement and doing a closed loop system that was gigantic to make 2 megawatts of power. It's tough in these colder areas.
Yeah, and just to follow up on that, the Piceance, the Williston, the Denver Basin, and the Gulf Coast seem to be kind of the 4 sedimentary basins that, you know, don't have ongoing volcanic activity or crustal extension that seem to be, you know, the hottest for geothermal. I say that temperature-wise and pun intended there. But those are really the 4 basins that people have been considering for their geothermal potential in sedimentary basins. But even still, getting down to hot formations, like a lot of people might know here, coming from the oil and gas side of things, since these are traditionally oil and gas basins, getting down to the 250 Fahrenheit, 300, 350, 400 is very deep and may not even occur until you drill through the entire sedimentary package into the basement rock. So just getting to those depths in sedimentary basins is a little bit challenging because they're older and they're colder and they've dissipated a lot of heat, unless there's kind of some specific sedimentologic and stratigraphic things that are trapping heat within these basins.
Excellent. I think we have time for one more, maybe 2. So there have been a lot of questions that have to do with essentially the cooling of either the reservoir or cooling of the fluid as it's produced. What can you say about that in EGS?
I
can comment on that, or Justin, go ahead if you want it.
I was just going to say, I mean, it is mining heat. You are going to deplete it. And at this point, you know, depending on what your project time horizon is, if you 10 years, 30 years, whatever it is, once you deplete that heat, you're going to have to drill more wells, close in the old ones, maybe wait for the rocks to warm back up. Induction's a slow process. We've been talking about combined storage EGS systems where you're actually using something like solar heated water re-injected into these reservoirs with your return fluids to potentially sort of maintain that reservoir temperature where you need it to be, you know, using power from off-peak time or excess wind or excess solar, that kind of thing. But yeah, it's mining heat. You will eventually deplete it.
Yeah, 100%. I agree with you, Justin. I just want to add to it that in shales or in oil and gas, you produce this commodity and there isn't that power plant on surface that you invested in, right? You just take it and you go and sell it somewhere else to get it refined, et cetera, et cetera. But in geothermal, upfront, you wake up on day 1 and you put that money for the wellbore infrastructure and you put that money for the power plant. Turns out the power plant could be like plus minus 50% of the total overnight cost. So wells if you look around the literature, people would tell you, depending on the EGS configuration you have, you could live between 3 and all the way to maybe like 13, 15 years, right? But no one would tell you it'll live to 20, 30 years. You'd have to do a lot of homework that we haven't showed or validated in the field to get to that extent. And hence, redrilling is inevitable, which sounds like a shales exercise. Every few years, you go ahead and redrill the same well. So it's nothing that is abnormal, but rather manageable and expected. And there's a lot of heat in place. I think that's what we emphasized on. Even on the same parcel, you exploit the 2 or 3 kilometers, you're not done. You can go to 4 and 5 kilometers, which is amazing. So there's a lot of work that can be done to show the value of EGS and geothermal in general.
Yeah, Eric Burns just texted me to say there's a lot of heat out there. Like even our estimates, we're only looking at 0.5% of it. So if you have to drill more wells to get more energy, it's not like there's one EGS installation you can put in a basin the size of, I don't know, the Haynesville or the Michigan Basin. You know, there's a large volume of rock and there's a lot of heat to be extracted. However, any individual, you know, system, you know, doublet or whatever you want to call it, you are going to cool those rocks down as you're producing. It's just the thing to keep in mind.
And it, you know, of course, that'll be variable based off the lithology that you're in, the thermal conductivity of that rock type, and you know the thermal history of the region you're in or the basin, of course. And then people have talked about, you know, well, can we kind of manage the reservoir differently, produce wells for 15 years in one area, and then switch to a different set of EGS wells, you know, a couple miles away, that sort of thing. So maybe there is a reservoir management strategy here as we get into, you know, what we might even call like secondary recovery for EGS. But, you know, that's something we kind of have to figure out as we're developing these projects.
That's good.
I want to, if we have time, Susan, I want to touch on what Eric said. I think it's a beautiful, important point. That is reservoir management. A lot of the technical challenges, which we talked about, have to do with this inability to efficiently extract or recover that heat that you have between these 2, 3, 4, 5 wells. And there are different techniques that people are proposing to make sure that you don't have this shortening of thermal longevity due to a highway, very high hydraulic conductivity fracture that just takes over all the flow and cools you down too fast. And there are many solutions that people are even wanting to test, my understanding, in places like Forge and others, that involve flow control devices, which is not a new technology, to be honest. It comes from oil and gas, and it happens that it's also available at very high temperature ratings. So why not? There are solutions that could extend this thermal longevity for sure.
I mean, that's so super interesting because if you could have chokes and they're automated through monitoring, it could be a really nice solution. But at any rate, so these are wonderful comments, wonderful presentations. We want to thank our presenters again, and we're getting close to, we could still be here another hour or two answering questions. So I just want to let people know that you will be getting an email with a link to the presentation. If you have unanswered questions or just have some comments and you'd like us to reach out to the presenters, please email education@aapg.org. And then we can direct the questions. We'll also know whether or not there are slides available. So I want to thank everyone again. So thank you, Nicole and Eric, Justin and Jabs. So it's fantastic. And just want to go around and give each person one little final word. So Nicole?
Thanks for joining us today, and we hope to have you engaged in other activities that we're putting together and spreading the geothermal knowledge.
Eric?
Yeah, thank you as always. We wouldn't be doing this if there wasn't a lot of interest in EGS and everything geothermal. And my closing thoughts are, you know, these projects are still very much exploration projects. You know, we haven't gone to full field development for any of these things. And we really won't learn a lot about how to make these projects in sedimentary basins, AGS projects, super hot rock, all of these different types of geothermal systems. We really won't learn about how to properly develop them until we put bits in the ground and start turning to the right. So that's really what we have to start doing now with these different projects.
Thank you. And Justin?
I just want to thank everybody for sitting in, listening to us, and for all your great questions. I would direct anyone who's interested in learning more about USGS work in the Great Basin and elsewhere to our publications in geothermics and in the geothermal rising proceedings. And there'll be quite a bit of content. Our people are presenting at the GRC conference in Reno this year. So if you're interested in basin modeling applications in weird places like Mars crater basins and, you know, across the US, come check us out.
Great, thank you, Jeff.
Yeah, thank you everyone for joining us today and for the opportunity to speak about EGS. I'd like to invite you to check out what NREL does for both subsurface and surface as well when it comes to technical economics, as well as value of EGS and other geothermal resources to the grid and how it could integrate optimally. Yeah, I think there's a lot of potential for EGS and equally a lot of challenges, and I'd invite you all to reach out and work on them.
Great. Well, final thank you to our panelists, and thank you to the AAPG Energy Minerals Division, Geothermal Committee, and a great thank you to our host, Halliburton. So goodbye. Thank you.